Okay, so welcome back. It seems like you're all doing well on your projects. Lots of exciting systems being developed, and we're looking forward to hearing about those. This is my last lecture, and I want to cover 2 or 3 topics. So the first one builds on where we were at the end of my last lecture. So if you remember, we had used a method in order to work out all the possible options for deploying an application on a set of clouds so as to meet security requirements for that application. And this was the last slide that I showed. And so we have 4 possible options. So there are 2 clouds, a green one and a red one. And we could deploy any of those 4 and still meet the requirements. So the question is, what do we do? So we could just pick. So we could throw a dice and pick one of those 4. But we would like to have somewhere to make a better decision as to what we should do. So the question is, can we automate the process of selecting the correct way to map this workflow over a set of clouds? And I said at the end of the last lecture that there's probably 2 of those that if I'd shown you the workflow, told you there was 2 clouds, a public cloud and a private cloud, and asked you to work out which ones were possible, I reckon you would probably have all come up with number 1 and number 4. So number 1 makes a lot of sense, because what happens is that you do processing on the private cloud of the high security healthcare data until you've anonymized it. At that point, you transfer the anonymized data over to the public cloud for analysis. And that's probably a very sensible approach, because what's happening is that you're using the advantage of the public cloud for the analysis, which is where you want the scalability. The first stage in that workflow of just anonymizing the data is very quick. So you can see why that's a good approach. The bottom one, number 4, that works, but it doesn't make any use of the public cloud. So you don't get any of the advantages of scalability and performance from that. But how do we decide which one to choose? This is quite a simple workflow. Sometimes we have workflows with 20 different services in them, very complex connections between them, and we might have 3 or 4 clouds on which we could deploy the application. So doing it by hand, expecting a human to do it and choosing the best one is not a good approach. So what the challenge we had was, can we build a tool which automatically deploys the application across a set of federated clouds? But the question is, how does it pick the best option? So as I say, we could use a developer or a security expert to choose, or we could introduce a cost model. So the cost models are used right across computing, and the idea is if you have a set of options, then you have a cost model which works out which is the best option to use, the option which best fits the criteria that you have. Now, the problem is that there's not just one cost model. We might all have different needs. For example, if we were trying to minimize time to do a set of computations, we might choose one solution, whereas if we were trying to minimize the cost in rubles of an option, we might choose another solution. If we were trying to come up with the most dependable solution, we might choose one option. If we didn't care about dependability, we could do something else. So you have to know what these requirements are. And these are usually called non-functional requirements. And sometimes people think about them as SLAs, so a service level agreement. So you state what your requirements are, and then you have a cost model which works out how to meet those requirements. And so we use this sort of model here, where you've got your application in the top left, and then you've got your requirements in the top right, which you specify. And then you have what we call a policy manager, which works out how to split that application across a set of clouds in order to meet the requirements. And we've done work on doing this for performance, and doing this for price, and doing this for dependability. But I will use as an example one of the simplest ones, which is doing it on price. So how many rubles do you actually pay? So in order to do that, we need somewhere to work out for all of those options that we have, in the case of the running example, those 4 options, what the price of each option is. So for that, we need to understand how cloud providers charge for their clouds. And in the main, this is the sort of way in which they do it. So they charge you for an amount of CPU. So this is proportionate to the time that you're using those CPUs for, and the number of CPUs, the number of nodes that you're using on a cloud. And they charge you for data storage, and again, it's based on how much data you have, but also how long you want to store the data. And then finally, cloud providers charge you for data coming in and out of the clouds. Now, in the main, as it says there, transferring data into a cloud is usually free at the moment. I think that's because cloud providers are very keen for us to put as much data in the cloud as possible, and then to analyze it there, knowing that they will then get some payment from storage costs and processing costs. But almost all the cloud providers charge you for extracting data from the cloud. And if you ever want to know how much this costs, then, for example, let me see if I can get this to come up. So if I do this, Control P, extend. No, it's not going to work. Okay. So there's a web page which I was going to show you. It doesn't really matter, but which for come up again, yeah. Which for Azure tells you how much you're going to pay for each of these different categories of costs. And there's a similar one for Amazon, and a similar one for OpenShift, and so on. So if we look at each of those different categories, so this is how we might work out what the cost would be. So this is the this is the data storage cost. So for each item of data that we have in our application, then if we can estimate the size of it, and I'll talk about how we might do that later, and we multiply that by the length of time which we need to retain that data, the length of time for which that data is stored, then we multiply those two together, and we multiply it by this E d.s figure, e to the p d.s, which is what I'm using as the unit price for storage that the cloud provider is charging. So this is what you can get from the website of the cloud provider. So let's say that it's 2 cents to store a gigabyte of data for a month. If we want to store a piece of data which is 10 gigabytes and we want to store it for 2 months, we'd multiply 10 by 2 and multiply it by 2 cents, and we come up with, what's that, 40? Never do calculations in the middle of a lecture, you always get them wrong, but it's something like 40 cents it would cost you for 2 months for that sort of data. And then to that, we need to add the CPU cost. So for each of the services that we have in our application, if we know how long that service runs, if we've got a good estimate for that, then we can multiply that by the cost that is charged for a unit of CPU by the cloud provider to find out the total CPU cost for the particular application execution. And if you're interested in how you estimate CPU costs, for example, then we had a paper at the supercomputing conference last year on how to do this, and there's been quite a lot of work in this area over the years. And finally, you get the data transfer costs. And as I say, it's not one cost for transferring data in and transferring data out, so that's why we have these two costs, which is the DXO, which is data out, and DXI, which is data in. And that's proportionate to the size of the data that you are transferring. And as I say, usually DXO, transferring data out of the cloud, is something that's charged for, and DXI, data into a cloud, is usually free at the moment. So what you need to do, what you can do is for your application, say for your workflow in eSign Central, you can take this cost model and you can work out, given the data that there is in the application, given the services, and given the transfer of data between clouds, you can work out a price for the execution of one of those workflows. And if I do this for the standard healthcare application which I've been using, then you can see that it breaks down into a particular, so these are the characteristics of the services. So service 0, the CPU time in seconds is 1 millisecond. And for service 2, it's 10 milliseconds. And for service 3, so service 3 is the one that does all of the analysis of the accelerometry data in order to come up with some results about the patient's health. Then that takes about a second. And then service 3, which just stores the data, that takes, again, about a millisecond. And then for the data, the size of the data that we get from these accelerometers is usually around a gigabyte, so you can see that's where those ones come from. But we don't need to store the original data in the cloud for very long. We don't need to store the anonymized data, but we want to store the results. The result of the analysis, which is actually quite small. It's only a hundredth of a gigabyte, 10 megabytes. We want to store that for a long time. So what's that? In months, 12 months, so a year. So we characterize our application like this. And then what we need to do is to get the specific costs for the cloud that we have chosen to use. So I'm going to give two examples of costs. So let's imagine that the public cloud and the private cloud in this case have exactly the same costs. And I've just used very simple values, not from any real cloud provider for this. So I've just used 10 somethings, let's say, cents per gigabyte month for storage, 1 cent per gigabyte transferred in, a cent per gigabyte transferred out, and 10 cents per second for execution time. And so if we do that, we can then go through all of these different options, and we can come up with those costs, which I hope you can see on the right-hand side. So those are the costs for each option. So the top row of that table is the cost for option 1, and the bottom row is the cost for option 4. So you can see that from that, which one's the cheapest? Well, it's the bottom one that's the cheapest, narrowly the cheapest, 11.32. Why is that? Why does that one come out the cheapest? Exactly. So all of the costs for both clouds are identical for CPU and for data. The costs for transferring data in and out were also identical, but the bottom one is the only one where you don't transfer data between clouds. So if that's the cost model that you have for the clouds, anything which keeps all of the application in a single cloud is going to win. Okay? So that's why that one is the number 4 wins. It's the cheapest. If instead we go to another pricing structure for these two clouds, so if we say that actually the public cloud is cheaper for storage and cheaper for CPU than the private cloud, although we'll say that the cost of transferring data in and out is the same, then what would we expect to happen? Well, what happens here, again, we've got the table at the top right-hand side, and you can see from there that now it is option number 1, which is the cheapest. And why is that? Well, that's because it does the minimal amount of work on the more expensive private cloud, then it transfers the data as soon as possible to the public cloud and does the analysis and long-term storage on the public cloud. So that's why that one comes out at 7 point something, whereas the option 4, which was the previous winner, is 11.32. So option 4, although it doesn't have the transfer costs, it's got the more expensive costs for storage and processing. So we can add this cost model into our tool. So again, I have this Haskell program which I use to implement the tool, and you can feed in the values for these costs into it, and you feed in the security requirements, and you press a button, and it works out which is the best option. And once it's decided on the best option, then it can automatically deploy it. So what we, in fact, do is, if you look at this, then that's the previous slide. What happens is that policy manager, having worked out what the best option is, it then works out how to create those partitions on the different clouds that it's decided to deploy the application on. So, as I said in my first lecture, eSign Central, as well as having that web-based user interface, which you can use as a human to do everything like store and analyze data, that's which you may have used if you've gone through the tutorial which was in the project list. So you can do that as a human, but we also offer a REST-based API. And you can describe the workflows using, it's actually a JSON data format that we use. So the policy manager takes in a description of the workflow in this JSON format. It computes the options for that workflow which meet the security requirements. It applies the cost model, works out what the best way to partition it is, generates the partitions, and using the eSign Central API on each cloud, it then deploys the application and causes it to be executed. So, and we can do that because eSign Central is very portable, so we can run it on, as I mentioned before, Azure, Amazon, OpenShift, or private clouds, or even Raspberry Pis as well. I don't know whether Raspberry Pis are they known in Russia? Yes. So it's very small, cheap devices. They cost, in England, they cost about, well, that'd be in rubles, something like 2,000 rubles, something like. Okay, yeah, but so 3,000 to 5,000 rubles, so about that cost. These very small little systems that you can use with sensors on them, again, we can run eSign Central on that. So using this policy manager, we can partition the application and deploy it and execute it. But as I've said, this is just one cost model that you can use. So, for example, there's some people at Sydney University in Australia who've been working on a cost model based on performance. So you can tell it how long you have to run your execution, the execution of your workflow, so when you need the results back, and it can then work out what the best way to deploy the system is in order to meet those requirements. And once you've got these different sorts of models, you can then combine them. So you could say, give me the fastest way to execute this application for less than $1. Okay, and the system can work out all the different possibilities in terms of how long an option is going to take and how much it costs, and pick the one which meets those requirements. So I've shown you a simple cost model, but you can add in other more complicated ones if you wish. Yes, sir. Yes. So it's not uncommon to have more than one private cloud because organizations, let me go back to I just need to go back here, in fact. So, as I mentioned at the end of the last lecture, organizations, when they see these options, they might think, well, this is very worrying, because if my private cloud fails, remember the private cloud is the red cloud, then there's not a single option which meets my security requirements. And therefore, I will create another data center, run that as a private cloud, and work out different options which you could use. And that means that if a private cloud fails, you've always got an option of doing the work using the other private cloud. Similarly, it may be that different public clouds have different costs, and therefore, for a given application, one application may be cheaper on one cloud than another one, and therefore, again, you can get the system to work out what's the cheapest way to do it. So all of the method and the tooling that we have, although I've made 2 simplifications in the examples, I've only used 2 security states, 0 and 1, but the method works from 0 to infinity, so you can have as many different security states as you want. And secondly, in the examples, I've only shown a public cloud and a private cloud, but you can freely mix and match them. And I have a PhD student who's working on, for example, systems where you might have, you're collecting data from a set of sensors, and I now know that from Jeffrey's talk yesterday that this is called a fog. So you may have a fog of sensors, each of which can do some sort of computation, but these sensors are coming in and out, perhaps as the connectivity between them comes and goes, perhaps because of weather conditions. And so what you want to do is to then be able to work out at any time which is the best way in order to do your application, even when there are clouds, in this case these sensors running east side central, when there are these clouds which are coming and going. In his work, when a cloud fails, it generates an exception, and when a new cloud becomes available, it generates an exception, and that calls the tool to be rerun. But instead of starting from the beginning, the tool starts from the current state of the computation and tries to move forward from there. Okay. Any other questions? Yes, yes.
You have to somehow solve this into the real conditions.
Yeah, that's very good. So, my PhD student who's working on this, these clouds coming in and out, he's having to explore optimization techniques which generate an approximate result, which is good enough, rather than do what I've shown you here, which is to work out every single option. No, I know that, but there are various techniques like greedy algorithms and branch and bound and so on that you can apply to this, which allow you to get a reasonably good answer in a sensible time. It is an interesting theoretical problem. I'm not sure yet whether there's anything you can do other than pick a good existing algorithm like the greedy algorithm or branch and bound or whatever in order to solve this. But it is a theoretical problem that he's addressing. In fact, we're writing while you're doing your project, I'm editing his paper on it, and we're hoping to publish it in the next month, so you'll be able to see that. Any other questions? Okay, so this is the end of the security part. I've got a few more things to say, but looking at other things that are going on in the world of security, I've just talked about multi-level security. There's lots of different work on security. I just wanted to give you an awareness of other things going on, because I know a number of you, from talking to you at the opening party, work on security. So here's ways that people are using in order to address security issues. So you can obviously encrypt data. So encrypting data as it travels over the internet between your organization and the public cloud is one thing that people do. Now the question is, what happens when it arrives at the public cloud? Okay, so if you're just wanting to store the data, and many companies are using clouds as a kind of backing storage, secure backing storage, because that means that if there's something happens, like there's a fire in their organization and they lose their data center, then they're confident they can get it back from the public cloud. And if you're just going to do that, you can afford to encrypt it because you're not going to do anything with it when it's in the cloud. Okay, it's just going to sit there. Things get much more difficult if you want to do processing of the data in the cloud. So a lot of the time, people decrypt the data once it arrives in the cloud and hope that they can build and that the cloud providers can provide them with a secure enough infrastructure which means that the data won't be attacked. So those are people, organizations who worry more about the transfer of information over the internet and somebody snooping on it there than they do about the security of the cloud once the data has got there. If you want a really hard research problem to keep you occupied for the next 10 or 20 or 30 years, then the bottom one is probably a good one to focus on, because there are people who do work on algorithms on doing computations on encrypted data. Okay, so this is where the data is always encrypted. You never decrypt it on the cloud, and you have to modify the way you do computations such that it deals with encrypted data and can return encrypted results. And this is for people like yourselves who have got a very good mathematical background. This is an interesting challenge, and there's been quite a lot of work in recent years. But at the moment, there are two restrictions. One, there's only certain types of computation that you can do in this way. And secondly, it takes an awful long time. It's very slow compared to conventional ways of doing computation on data. But somebody here may be able to crack one or two of those problems and solve this problem. Okay, so the conclusions from this part are that security concerns have been known to deter organizations from using public clouds. I think this is getting less and less. I think organizations, when they balance the advantages and the disadvantages, they're becoming more comfortable with it. And we saw that when I gave a list of the different types of applications people now trust to clouds, which included, in some cases, healthcare, in some cases, salary and payroll information about employees of organizations, and in some cases, with CRM systems, information about all of your organization's customers and what they buy. So I think things are slowly changing. But there has been this reaction where, in order to try to counter this, some IT departments within organizations have proposed private clouds. So using their internal IT in a much more agile way to try and mimic some of the characteristics of the public cloud. However, of course, there is this limitation on scalability. You cannot just keep adding nodes to your private cloud dynamically without somebody writing a check and a piece of hardware arriving and being added to the servers which are in your basement. And in my experience, there's always issues to do with the amount of space that there is in the machine room, how much power there is available to power the new kit, and how much air conditioning there is to keep it cool. So it often takes quite a while from realizing that you need more power in your private cloud to actually getting that power. So this is why federated clouds have become popular. So people thinking about, well, let's have a private cloud, often our existing infrastructure that we've already invested in. We've invested in the hardware, we've invested in the people to manage it, and we'll use that for those cases where we're concerned about security, but we'll then use the public cloud where we can take advantage of its scalability for data that we're less concerned about. And my argument is that the two things that you need in order to achieve this is, firstly, you need to have the same infrastructure on the internal cloud and the external cloud if you're really to be agile, if you're really to be able to make very dynamic decisions about what to deploy internally and what to deploy on your public cloud. And secondly, you need somewhere to automate the process of working out what the options are for distributing your application over federated cloud in order to, firstly, to meet your security requirements, and secondly, in order to minimize the cost according to some cost model. And so that's why in this lecture I introduced cost models. Okay, any questions about that before I move on? Yes? Yeah, so that's interesting. So that would be a more sophisticated cost model, and the way in which you pay for memory at the moment, so you're talking about main memory, the RAM memory, yeah, is that you pay for a particular sort of node on the cloud. So different nodes, depending on how much memory they have and how powerful they are, how many cores they have, you're charged at a different rate. And so it's different to the other sorts of costs. You can't dynamically acquire extra RAM memory. So how would you deal with that? Well, you probably need a more sophisticated cost model. You could model it by perhaps having a cost model which took into account performance, which took into account the memory requirement, and then you could, instead of, say, treating Azure as a single cloud, you could pretend that it was a set of separate clouds with for different sorts of nodes, with different performance characteristics and different costs, and then the sort of model that we have would generate the options. You would have a more sophisticated cost model which would take into account performance, and it would tell you which the cheapest way to do it was. Any others? Okay, well, let me finish with some other work that we've been doing. So this is work that we almost get as a bonus from what we've done before. So when you talk to scientists, then they're very keen on reproducibility. And in fact, it's very hard to reproduce experiments, but this is the sort of litmus test for science. You do some experiments, you publish a paper. If it has an impact, if people are interested, then other people will try to reproduce those results. And the question is, how can we do that for systems where we're doing the science on a computer? And it's not easy. So this is a figure from an interesting paper by some colleagues at Manchester. So they work on a workflow system called Taverna, which is probably in the top 1 or 2 for e-science workflow systems. And somebody went and had a look at workflows a few years after they had been uploaded into a system called My Experiment. So My Experiment is a very nice idea. It's a place on the web where if you have a workflow, you can upload the description of the workflow, and the idea is that other people can use it. And it's got very nice social media side to it, so you can share with other people comments or ratings for a particular workflow. But what they found was that within about 5 years, 91% of workflows had failed. And this is a real shame, because it reduces two things. It reduces reproducibility, because if you try to reproduce an experiment that uses the workflow and the workflow won't run anymore, then you can't do it. But also because it discourages sharing. So it's always good if we can share what we do in science, share data, share computational methods, and sharing workflows would be a good way to do that. So why is this? Well, it's because if you look at the way that a workflow engine like Taverna is organized, then what it does is it does what's often called choreography. So it sits on your laptop or your desktop machine, and other people expose services. So they publish services as REST services or as web services or some other type of service with a standard interface. And then you create your workflow, and Taverna has a very nice workflow editor which then calls these services. So what's happening is that the workflow engine itself, its level of control is within that blue circle. It has no control over the services that it calls. They are often spread all around the world, and all you can do is send a message to them and get a result back. And why does this fail? Why do these workflows fail? Well, it's usually because of some problem with a service. So there's usually two reasons for it. So somebody improves the service. So they add some capability to it. Perhaps they change the format of the output or the input. But what that means is existing workflows which use that service will now fail. And the second reason is that a lot of these services are done by people like yourself, PhD students, and once you've done your PhD, you switch off your desktop machine and the service that was on it just goes. Okay? This happens quite commonly. I've overheard conversations with people phoning up some lab that were offering a service and somebody was using it as a key part of their own PhD, and it turns out that nobody there has a copy of this service anymore because the PhD student who'd created the service and who was managing it had left, and the desktop machine had then been rebuilt for somebody else, for another PhD student, so it's gone, and that's the end of it. So what we can do instead, one of the reasons we were interested in eSign Central was because we could have control over more of the key entities which you use in executing a workflow. So not just the description of the workflow itself, but we wanted to store the data, so we do that in eSign Central, but also the services. So in order to dynamically deploy the services, we had to have a repository of services. And so this is what we've been trying to do with eSign Central, and I'll talk about some of our experiences with it. So what we're trying to do is, if you think about the three key entities for workflow-based eScience, then you need to store the data. And the systems like Dropbox or repositories in universities which will allow you to do that. You need ways to store workflows, and my experiment, which I talked about earlier, does allow you to do that. And you need ways to store services. And this is where there's a bit of a gap, and this is one of the things that we've been addressing through the work we've been doing. From talking to Jeffrey, this seems to be a more active area of research now, given the cloud. And so there are other groups now trying to find ways to build repositories of services that can be dynamically deployed. What we've found is that the key thing to reproducibility is versioning. So people will update services, they will update data, they will update workflows, and I don't know whether if you played with eSign Central, one of the things you'll have noticed was that whenever you look at some data, or whenever you look at a workflow, or if you look at a service, then it will tell you what version of that data workflow service it is, and you get a drop-down menu which allows you to go back and select a previous version of a service. So you can always rerun workflows using exactly the versions of the data and the service and the workflow which somebody had used previously. But you can also try different versions of services. So quite often, somebody will improve a service, say its performance or its capabilities, and so you can rerun your workflow, say just try the different version of the service, the latest version of the service, and check that you get the same result. So you have these capabilities, but you need some way to glue these together. If somebody says to you, I've done this experiment and I've produced this data, and you want to reproduce that experiment, what you need to know is exactly how that data was produced. The workflow, the services, and the data. And for this, you need provenance, which Sergey talked about yesterday when he talked about reproducibility. So if we want to know for anything in our system what the version, how it was produced, then we need to record provenance information. And there's a bunch of other things we can do if we have actually got that, and I'll talk about some of those. So what we do with eSign Central is anything that goes on in the system, we log it. So we have a database which records who the user was, what the workflow was that they ran, what the data was and the versions of that data, and what the services were, all versioned. And we create from this a provenance graph. And we store this in a database called Neo4j, which is a graph database. Why do we pick Neo4j? Well, it's because we know the chief scientist very well, who's one of our PhD students, and so he's been helpful to us, and it's a good system for storing and querying graph-based data. And we do this using a system called OPM. So there's now a standard for provenance, the Open Provenance Model, and so we record everything using this model. And you can see, you won't be able to see the details, but this is the sort of graph that you get from one of our workflow executions. So you automatically get this, and by clicking on a button in eScience Central, you can see that for any piece of data that you can find in there. And it shows the data that was used and the services and the workflow in order to generate another piece of data. One of the interesting things about when you're trying to compare the results of different workflows, perhaps with different versions of services, was that one of the things we found was that sometimes people would improve a service and we'd see whether we got the same result, and we didn't. And we look at the results and we discover actually the important information was the same, but perhaps some little bit of text around it had changed. So one common thing was that people would write services which, let's say, did some analysis, produced a result, but they also included text which told you the version of the services. So it's the analysis service 3.2.1, and the result is this. And of course, that meant if somebody changed the service, even if it gave exactly the same results, if you just did a bitwise comparison, you got a different answer. So what you have to do, if you want to compare different provenance traces, so here's two provenance traces, and the shaded areas show where the differences are, and what we can do is we can work out where the results diverge. So which was the first part of the computation which generated a different result. But if we want to check whether these results from these services are equivalent, then what you need is some sort of method so that you can do semantic equivalence. So we've had to add functions to do this, which can be service specific, but then they do allow you to compare the results of services. So a common example is XML, because if you just do a bitwise or a text-based comparison of XML, then it may look different, but actually it's exactly the same, because as you know, there are things in XML where you can change the order, you can put white space in wherever you want, and it doesn't change the meaning of the XML, but if you just compare it character by character, that makes a difference. So you have to have operators which produce a canonical, as it's called, a canonical version of the XML so that you can then compare it. And so we've done this, and if you look in my publications list, you can see papers where we built this system and we use it for reproducibility, but also to compare differences in the results of the computations. The other use for provenance comes from when we work with some large organizations. And if you're a pharmaceutical company, then you have to show you're working. Do you have that phrase in Russian when you're at school? If you get a mathematical question, you don't get as many marks if you just put the answer than if you show all of the stages that you went through to get to the answer. We say in England, we say, show you're working. Show all of the stages, not just the final result. And audits are a bit like this. So it's no good if an auditor turns up at your pharmaceutical company saying, well, we produced a drug based on this analysis, and here's the final results. What they want to do is to understand how those results were produced. And pharmaceutical companies have got into trouble before if they've lost some of the data that was used or some of the computational processes that were used to generate these results. And if you get into trouble, it can result in a multi-million-dollar fine. So there's a lot of money resting on it. And so provenance allows you to do this. So because you can automatically collect provenance for any piece of data, you know that you've automatically gathered the information. And this is an example of an area which has become more important, I've found in discussions with organizations about using the cloud over the last 3 or 4 years. So to characterize it, 5 years ago, only some organizations considered using the cloud. There were some early adopters, some pioneers who considered it, but a lot of organizations were quite conservative, quite reluctant. Then that conservatism went away, but now they've started to worry about governance. And the reason is that if you look at the way in which IT used to work within organizations, you'd have an IT department, and if you wanted to store some data or if you wanted to run a new application, if they were a good IT department, then they would get you into a room and they would ask you lots of questions about governance. So I've written some of the ones up there that are quite common. So you can see they want to know something about do we need quotas, because there might be a danger that some users will use up all of our space. What about sustainability? How long do we need to store this data for? For example, for some sorts of financial audits, you need to store the data for 7 years. Quality of service, security, what sort of security restrictions? Can anybody in our organization access this, or only some people? Dependability, how reliable does this have to be? Because as you know, building reliable computer systems is more expensive than building ones which, if they fail, it doesn't really matter, because you can rebuild the systems and start again. And performance, how fast you need to get these results. Does it really matter if somebody tries to do something and it takes an hour rather than a minute? So IT departments, good IT departments, would ask these questions, and then they would build a system to meet those requirements. And then along came clouds, and some organizations, with some parts of an organization, either individuals or divisions of an organization, these pioneers would start to use clouds, and they would just do it. And quite often they were praised. I've known people who've got pay rises because they managed to do something very quickly in the cloud where it would have taken a long time to do it through the IT department. For example, where the IT department would have to buy extra machines to run a new application, that would have taken months, whereas somebody's just gone onto a cloud, uploaded the data and done the analysis. But you can see the problem. There's none of those discussions with the IT department who are experts on governance, and in a lot of cases people didn't think about governance, so they wrote code in the cloud which didn't obey security requirements. They didn't store the data in the cloud for as long as was necessary, and so companies have got into trouble because of this. So what do we do? So the thing that we often are doing with organizations is that talking to them about how we can use a cloud platform in order to add this level of governance which was previously added by the IT department for its own internal IT. And I think the tension here is because individuals just in organizations often just want to get on, grab some cloud storage, grab some cloud processing and do their work. They don't really care about governance. It's the organization which gets fined if there's problems with governance. And so there's this tension between the IT departments and these people. And it comes into universities as well. I've heard the head of a major UK university say that he's very worried about meeting his commitment for storing data for a particular length of time. So there are some funders in the UK, and I'm sure it's true in other countries in the world, where nowadays if you read the small print of a contract, the letter you get if you get a grant, what it says is that any data that you produce you have to retain for a particular length of time and make available to others. And the head of this university, it would be the university which would be fined, they may be banned from accessing funds from this particular fund awarding body unless this requirement was met. And so it's the head of the university who was very worried about people in the university just going out and using a cloud. At the end of the project, forgetting to keep the data, just stop paying their cloud bills, and the data goes, and the vice-chancellor is fined or sent to jail or whatever. Vice-chancellors worry about things like that. And even in researchers like me often worry about the size of the credit card bill that my research group gets at the end of the month, because of all of our clever research students are finding new things to do on a cloud. And it can go up and up and up, and sometimes you're never really sure why. So even for research groups, it can be a concern, this lack of governance. So if you have a platform, and again, I'm talking about eSign Central, but I'm using that as an example because we've used that to explore these issues. If you have a platform, then can you add this level of governance? Well, there's a possibility of doing it because users access the cloud through the platform rather than directly. And so your platform can add this level of governance. So if you get something like this with a platform, then people in the organization don't directly go to the cloud. They use the platform, and the platform can meet exactly the same levels of governance. So we've started to do work on adding things like quotas, adding policies for how long data should be retained, using provenance in order to give you that audit trail so that organizations can always show an auditor exactly how data was produced. And of course, from the work that you've seen in this and the previous lecture, also the ability to make good use of lots of different sorts of clouds in order to reduce costs and meet performance, reliability, and security criteria. So this is, I think, where we will go with clouds. I think the higher level platforms that are being provided on clouds will offer more and more facilities to allow organizations to meet their governance policies rather than allowing individuals just to go and do whatever they want on their cloud. And so, for example, just a minor example, if you've used eSign Central, you may have noticed that there's a quota, and we can control how much storage and how much processing people can use when they go through the system. Okay, so I talked about this because this is something that we're seeing some trend in governance, and it's something that over the next few years you will also, I think, see as you go and become academics or go out into organizations using the cloud. But a lot of what I've talked about, it turns out, comes down to some of the abilities which we introduced into our platform in order to allow it to scale. So in order to allow it to scale, we had to have ways of keeping storage of services, workflows, and data so that we could then dynamically deploy them across a set of nodes. And if you do that, then you also get these other opportunities, including the security opportunities to use federated clouds in order to meet security requirements, and also to give you reproducibility by rerunning workflows irrespective of how long ago that workflow was run, and irrespective of what versions of services or versions of data were running at that time. So, in my opinion, dynamic service deployment is something that's very important for clouds and something that's going to grow in importance over time. I also feel cloud platforms can offer governance, which again, as if more and more organizations are going to use clouds for a wider range of applications, including some that are sensitive, like pharmaceutical companies developing drugs, for people storing healthcare data, then having this governance is going to be important. And I think, again, this is something that cloud platforms can add. And finally, I've used eSign Central as an example. I'm not claiming it's perfect and it's solved all the world's problems, but it is the vehicle that we've used to do experiments in all these different areas. And if you haven't done it, you can always give it a try in the project description. I've got the URL of a free version of eSign Central, which you can just go on the web and use anytime you want. But also, if you want to use it, then it's available to download it's on SourceForge. So just search for it on SourceForge, and you can download it. You can run it on your laptop or on a set of servers, or on Azure, or Amazon, or OpenShift, if that's what you want to do. And if you do that, let me know and get in touch, because it would be good to keep links up to if you're working on eSign Central so that we can perhaps work together. Okay, thank you. Okay, any questions before lunch? Yes? Yes?
You have some metadata or something else which may help to find competitor workflow.
Yeah, so if I can get this to work again, let me have a look. Yeah, so you can't really see it very well, but that's the provenance graph, which is automatically collected and created every time you do anything on eSign Central. And if you could read it, it would tell you who the user was. It's a user called Hugo Hayden on the right-hand side, and it would tell you the workflow, it would tell you the version of that workflow, and it would tell you all the services that were executed in that workflow and the versions of those services, and it would tell you all the data that was used as input and all the data that was used as output. And so then you can click a button to rerun that if you want to, and it would run exactly the same version. We also have an extension, because what we find is sometimes people run one workflow that creates some data and then run another one and another one to chain these together. We also have an extension so you can combine these workflows based on the provenance traces of how data was created. So you get what the question you asked, you get it for free as long as you collect all of the provenance. And again, whenever you're building a system, even in the 25, 30 years ago, and I worked in industry, and we were building systems, we always logged everything that we could in order that if you ever had to, you could work out what went wrong or what was taking time, or you could try to improve things. And so collecting provenance is the modern version of logging everything that you possibly can. I think this, that approach of logging continues today. So as I understand it, Facebook do clickstream logging. So every character you type, when you're interacting with Facebook, they record it and then they do all sorts of analysis on it. So this is perhaps the science equivalent of that. Any other questions?